try. So, as Konstantin said, I will talk about relation between indecomposable characters and invariant ergodic methods for certain full groups. So I will start with some basic definitions. Mainly, so one of the key objects is a Brattley diagram. So here is a definition, formal definition. What it says basically that we have a graph which consists of levels, both vertices and the edges. So we have level 0 consisting of one vertex with 0, and then we have some edges connecting to level 1, etc. So there can be multiple edges. It's possible that between some vertices of consecutive levels there are no edges. So this is basically a definition. All levels are finite sets, and for convenience, we define a range map and a source map, denoting the lower and the upper vertex of a given edge. Next. We will call a finite or infinite sequence of edges from consecutive levels a path, well, when it's connected set of edges. Notice that we call, so a path only is allowed to go in one direction down of the graph, starting from some vertex. So if we go first down, then up by some different edge, we do not consider this a path. So just convenient definition. Now, for a Brattley diagram B, we denote by xb the set of infinite paths starting at the vertex v 0. So something like this. Here, then somewhere else, etc. To infinity. We know this path space. So this is a standard Cantor space. We know this space with a topology of cylinder sets. So the open sets here, the base of topology will be consisting of cylinders, that is the set of paths starting with a given finite path. So we go following these edges to here, and then after that we can go everywhere, and this will be set U of E1, E2. So the usual definitions. Next, we introduce groups of permutations of paths, namely for each integer n, Gn will be the group of permutations of initial n segments of the infinite path. So given level n, say n equal to 2, and given two vertices, say we start with the 0 and here, we are allowed to permute in any way the paths between these two vertices. So for instance, we can interchange these two paths, one going this way and another going this way. And the other edges we don't change. So we're allowed to change only the first m edges of the path. So this is some finite group Gn, which is a group of homomorphisms of the path space XB. And we denote by GB the union of these groups. We call it the full group, or approximately finite group associated to the battery diagram B. Initially, full groups were defined as groups of homomorphisms preserving either homomorphisms or Borel transformations preserving orbit equivalent relations. So initial definition was due to die, and these groups are similar in the sense that they have similar properties. For instance, given two sets A and B, such that one is larger by measure than the other, we can move one set A inside the other B by an element of this group. So this is a sufficiently large group. In this talk, we will assume that the battery diagram B is simple. This means that given an H, a level M, there exists a level such that every two vertices between these two levels are connected by at least one path. So it's possible that we have two levels such that some edges are not connected, some vertices are not connected, for instance, this one and this one. But the property is that there exists level M greater than N, maybe some large number, such that for any two vertices, there exists some path joining them. And this intensity of B is equivalent to minimality of the action of this group GB on this space XB. So this is not to be confused with the simplicity of the group G itself. The condition is different. Next, we noted that these groups Gn are products of finite symmetric groups. So each of group Gn is just product of groups of transformation on the set of paths joining two particular vertices. So product of symmetric groups. And another way of viewing this GB is as limit of finite symmetric groups on the block diagonal embeddings. So now let me talk a bit about motivation why to consider these groups. These approximately finite full groups arose initially from the study of orbit equivalence relation on counter minimal systems by for instance, Herman Putnam Scow, and also in papers by Giordano Putnam Scow, and has application to theory of sister algebras. So one of the results, for instance, is that minimal the systems are strong orbit equivalent if and only if the associated full groups are isomorphic as abstract groups. Moreover, the isomorphism of cross-product sister algebras is completely characterized by the strong orbit equivalence of the underlying dynamical systems. So this is a couple of words of motivation, and some important property, simplicity of the group GB. It's not always simple, but the commutator subgroup GP prime, this is the subgroup generated by elements of this form. It is always simple. This is known. These approximately finite full groups are also related to the so-called topological full groups. These groups are built from homomorphisms of a counter space X, denoted in this way, the homomorphism T with double square brackets. And they are, by definition, a group of homeomorphisms of X for which there exists a continuous function n of X, such that f of X at each point is of this form, t iterated n of X times. So n of X can be positive or negative. So basically, this is a set group of homeomorphisms preserving orbit translation in a continuous way. And given a topological full group using Kakutani-Laughlin towers, one can associate to it a Bradley diagram B such that GB, this approximately finite full group, will be a subgroup of T, of the full group of T, and moreover, it is a dense subgroup. So in my talk, I will focus on the approximately finite full groups. They are easier to study, but our ongoing project also proving similar results for topological full groups. So because of this property, because inside the topological full group we can find approximately finite full group, we can study also similar objects on the topological full groups. Now let me talk about characters and representations. I will just give basic definitions necessary for my talk. So first, by a unitary representation of a group G in a Hilbert space H, we will mean here a homomorphism from a group to unitary operators for Hilbert space. And here, Hilbert space is just linear space, typically infinite-dimensional, with a given positive definite quadratic form on it called scalar product. But for the purpose of this talk, we can just think about the following key example. So having a dynamical system, so consisting of space X with measure mu on it, and action of group G, measure preserving. We can consider the space H equal to L2 of X mu and define the action of G on the functions by shift. So if you're not familiar with representations, then this is a basic example about which you can think. Now, definition. Basically, a character on a group is a conjugation invariant function, which is positive definite in this sense that for any finite number of elements G1, Gn, the matrix consisting of these elements is positive definite, and also we require for simplicity normalization that the value at the unit element is equal to 1, the unit element of the group. And a character is called indecomposable if it is if there are no characters chi1 not equal to chi2 on G, such that chi is a convex linear operation of these two characters. So basically, it means that chi is an extreme point in the space of characters. So basic example of a character is given a finite dimensional representation pi of a group G. We can consider just the usual trace, matrix trace of pi of G, and this would be a character on G. What is more interesting for us is given a measure preserving action of a countable group G on the probability space X mu, the following function chi of G equal to the measure of fixed points will be a character. So here fix of G is just equal to the set of points which are fixed by the particular element G. So here the easy thing to check about this function is that it's conjugation invariant. It just follows from the measure preserving action. Not so trivial is positive definite. Sorry about technical difficulties here. And to show that it is positive definite, we associate to it a representation. There is a representation pi of G in the Hilbert space H and a unit vector psi, such that this formula is satisfied. The bracket here means just the scalar product, the positive linear, positive definite quadratic form. Now this representation can be constructed in the following way, using the so-called groupoid construction. We start with the space X tilde consisting of the pairs X, Y in X times X, such that X equal to GY for some element G in our group G. So basically this is the orbit equivalence relation on X. Given a Borel set A in X tilde and the point X, we define by AX the slice, that is a set of points X, Y, such that they belong to A, so X is fixed, Y changes, and we introduce the measure mu on X tilde as mu of A equal to integral of cardinality of AX d mu of X. So this is also called counting measure sometimes. Now we define on L2 of X tilde mu the representation pi as follows. We act by element of the group on the first copy of X. So one can check that this will be a unit representation, and moreover, if we define by its side of x, y, the diagonal vector, the delta function of x, y, so it's equal to 1 if x equal to y and 0 otherwise, we will have this formula. This is just easy computation. The measure of fixed points of G will be equal to the scalar product pi of G psi just apply this formula. And this implies that this formula defines a positive definite function on the group G. Now we have this map from ergodic measures to indecomposable characters and then to representations. So having action of group G on X mu, we obtain character chi, and this triple representation pi in the Hilbert space H with a cyclic separating vector psi. It is known that character chi is indecomposable if and only if pi is a factor representation. So decomposability of chi means that it's extreme point in the set of characters, and factor representation also means in some sense that pi is extreme point in the space in the set of representations. And factor representation means that the one Neumann algebra generated by pi has trivial center. I will not go into details now this definition. I will not need it much for the talk. Now, so the interesting question is the relation between ergodicity and indecomposability, because ergodicity also a notion of extreme point in the set of measures. A priori, ergodicity of mu does not imply that chi is indecomposable. Moreover, for many groups, this correspondence is not surjective. There are many characters which cannot be obtained in this way. It can be, for instance, by obvious reasons. For characters, it's possible to have complex values, non-real values, but this way produces only real values, positive valued characters. So if our group is not simple, it's likely that there will be many examples when we'll have complex valued characters not produced in this way. But Anatoly Vershik suggested that for sufficiently rich countable groups, simple groups, every indecomposable character can be obtained in this way. And in my talk, I will explain that this is true for the full, for approximately finite full groups in some sense. And just for convenience, we call a measure mu almost ergodic if it can be approximated arbitrarily well by ergodic measures in the weak star topology. In this correspondence, we will allow mu also to be almost ergodic measure, not necessarily ergodic. Now, our main result is the following. So I think that we have a simple Brattley diagram, and let GP be the corresponding approximately finite full group, and XB be the corresponding path space. We show that Vershik conjecture is true for the commutator subgroup GB prime of GB. So it's like subgroup. It's dense in GB. But exactly, there exists k integer number, and GB invariant almost ergodic measures U1 so on UK on this one space XB, and numbers alpha 1, alpha k, such that for measure mu defined as this tensor product in this space with diagonal action of GB, will have this formula for the character. So all the composable characters on the commutator subgroup of the approximately finite full group have this form. So notice that here not only from this, but also we describe exactly what is the form of the measure mu. It will be this type of product for a finite number of ergodic measures, or almost ergodic measures. Moreover, every indecomposable character, every character defined using this formula is indecomposable, so this is a complete description. And finally, concerning the group GB, because the factor group, GB modular the commutator group, it's an abelian group. There can appear also some multiplicator, some homomorphism rho from GB modular GB prime to the unit circle. So the indecomposable characters are not exactly this form, but will have also some complex valued multiplicator. Previously, jointly with Medynets, we proved this for the case when the group GB is simple, that is concerned with its commutator, and XB admits only finitely many invariant ergodic measures. And now we generated this for arbitrary case, arbitrary approximately finite full group. So the only condition is that the diagram D is simple.
May I ask a question?
Sure.
Regarding number 3, you said Vershik had some conjecture that if GB is sufficiently rich,
And simple.
So in that case, can you get rid of the does this give you some more information with respect to this conjecture?
Well, it says that the conjecture is true for this class of groups, so for the
commutator
subgroups. Yes, the group GB is not simple, so we obtain some richer, slightly richer set of characters by this.
Aha, so because I'm actually asking about GB.
Mm-hmm.
If in some cases you will be able to get the same for GB.
Yes, exactly. When the group GB is simple, it can be described easily in terms of the Brattley diagram, namely, the group GB is simple if and only if for each level. So let me try to draw some picture to illustrate. So the property is that for each level M, there exists some level M greater than N, such that for any pair of vertices, the number of paths between them is even. So it turns out that this algebraic combinatorial property describes simplicity of the full group.
But wait, is this if and only if in the sense that if
yes.
If this condition is not true, there is no chance that that we will have such a representation.
Yes. I mean, it's just a simple difference. Rho of G is a simple object. It's a homomorphism from abelian group to the unit circle. So the difference is not very large. But there is. Okay. Now, in this general case, we need to develop some more general techniques, and the proofs are more complicated. And we started by investigating the ergodic measures on invariant ergodic measures of the action of GB on XB. Denote by M of GB the set of all invariant measures, by epsilon of GB the space of ergodic invariant measures, and we equip the spaces with the weak star topology. It can be defined in many equivalent space. So we can define, for instance, using semi-norms of the following form for any open set A. The norm of M, the norm of mu will mu1 minus mu2 will be sorry, the distance from mu1 to mu2 will be equal to this expression. And we equip the space of continuous, so we study continuous functions on these spaces of measures, keep it with the supreme norm. And for a open set A, we consider the function MA of mu equal to mu of A. So we have a collection of this function on this space of almost ergodic measures. They all have ranges between 0 and 1. And we introduce the space of continuous functions on almost ergodic measures with positive infimum and supremum less than 1. So one of the key results concerning them is that the set of functions is dense in the space of discontinuous functions on almost ergodic measures. I don't know if this is some typical property for functions in ergodic measures and this type of functions. But we need to work to prove it for our case. So the proof is based on several propositions, several statements. So first statement is certain multiplicativity property of these functions of measures on the global sets. So it states that if we have a global set B and we have a sequence Bn of Gn invariant sets. So then there exists a sequence of Bn of Gn invariant sets such that measures of Bn converge uniformly to measures of B for each ergodic, for almost ergodic measure. So let me just briefly comment what this condition of Gn invariance means. It means that our set Bn is union of cylinders of level m. So we have a finite number of paths joining somehow the zero level with the nth level, and after that the paths can be arbitrary. So this is how the set Bn look like. It's defined just by some finite number of paths between 0 and n level. And for any open set A, we have this property that measure of A intersecting Bn converges uniformly with product of measures mu A and mu B. It's kind of some property similar to mixing in some sense. We are moving set Bm to infinity. We're making it kind of mixing, and in the limit, the measure becomes product of measures for this set. Next, we define by d of xb the closure of the set of functions ma for a in xb clopen in the subnorm topology. And immediately we obtain that the set is invariant under pointwise multiplication. Next property of this function is if we have two sets A and B such that supremum of MA is less than infinitum of MB, then there exists an element G moving one set inside of the other sets entirely. So this condition means that for each measure mu of A will be less than mu of B. So this is a natural property, something classical. And finally, another proposition that for any functions f1, f2 in this space, and any alpha beta real numbers such that this combination alpha f1 plus beta f2 satisfies infinitum f is positive in supremum f less than 1, we will have also that f will be inside the space D of xd. So if we can approximate arbitrarily well f1 and f2 by the functions ma, then this linear combination also will be approximated arbitrarily well. So just a couple of words about the proof, just to give an idea. For instance, let's see how to go from function f to function 1/2. Forgetting that I have here nice pen. So f can be approximated by this functions m a. So we take a such that our function is sufficiently close to f. So we have some clopen set a. We take a large number n. The clopen set A will be union of cylinders of level n. And then for each vertex here of level n, we consider, so inside A will be many cylinders corresponding to paths between these two vertices, and we just divide this set of paths approximately in half, and take approximately half of this paths, puts them in B, so we construct a set B, which is in some sense approximately half of the set A, and then NB will be approximately equal to 1/2 of MA. So this is a simple idea. Next, if we have F1 greater than F2, we can easily as well construct F1 minus F2. We just approximate F1 by function MA, F2 by MB, and we have that MA is greater than MB, and this means that we can so the set B can be mapped inside set A by an element G, and we can define C as A minus GB, and then MC will be equal exactly MA minus MB, because the action of G is measure preserving. So this is some simple ideas we state in this proposition. So where is okay, well, it was here, and now based on this proposition, I can give a sketch of proof of this density statement that the functions MA here are dense in this space of continuous functions with values between 0 and 1. So we introduce the set D hat of functions which are of the form alpha F1 minus beta F2, where F1 and F2 are in this set D of XB of approximable functions. And from previous observations from these propositions, we conclude that this space of functions is invariant under taken linear combinations and products and is closed. And thus, it is a subalgebra of algebra of continuous functions on the space of almost invariant ergodic measures. Since Clopen sets separate border probability measures on the Cantor space, meaning that for any measure mu, we can for any two measures mu1, mu2, we can find the Clopen set such that mu1 of A not equal to mu2 of A. This space D hat separates points. Moreover, it is non-vanishing at any point, and it is the space of almost ergodic measures is compact, and so we can apply the Stone-Weierstrass theorem to conclude that this space of functions in fact coincides with all continuous functions on almost ergodic measures. Finally, given so this is space of all functions, but we want to restrict to the functions with values between 0 and 1. Now, for any function, we can write it by this in this way: alpha F1 minus beta F2 with F1 F2 in D of XB. But using this proposition 6, we obtain almost immediately that this implies F also inside D of XB. So this is finishes the proof of this proposition that any function in this space can be approximated arbitrarily well, but this functions MA or open set stage. So this finishes discussion of the measures. So this was the most important part about the measures. Now let me talk about the characters and factor representations. Sorry, this is a misprint. It should be chi. So now, starting from indecomposable character chi on the commutator subgroup, we want somehow to construct corresponding almost ergodic invariant measure on some space. First, there is a classical construction called Gelfand-Neumann-Siegel construction, which associates to a character a triple pi h psi, where pi is a unitary, in fact, factor representation in Hilbert space H, and psi is cyclic and separating vector such that chi of G is equal to this scalar product pi of G psi psi. So you probably this probably looks very familiar, but before we talked about this only in particular case when the character chi is obtained from the measure. Then we have H to be L2 space in certain topological space with an invariant measure, and then we have this function equation. So this is true in general. There's a more general construction called Gelfand-Neumann-Siegel construction, which gives us this representation. Now we want somehow to see global sets inside our representation. So for that we define for each open set a subgroup of elements supported in this set. And we introduce the orthogonal projection onto the subspace of vectors in the Hilbert space, which are invariant under the action of HA. So to explain this, let me give a simple illustration. So if we consider for simplicity, say H equal to L2 of XB mu, then G acts by shifts. We obtain representation by shifts. Called Koopman representation, and so for simplicity, let me represent XB as segment. So here in XB we have some subset A. HA is a set of all group elements supported inside A, so acting previously outside. So the space of invariant vectors in this case will be just the space of vectors which are constant on the set A. So this type of functions. And orthogonal projection PE will be just averaging of a function of a given function of this over the set A. So this is just to give you an idea what are these orthogonal projections. In general, they are more complicated. And by definition, the trace of an orthogonal projection is, in this case, given by this formula, scalar product of p xi with xi. It's an important function on von Neumann algebra. And one of the key statements in our proof is that for any group element, we have that the value of the character on this element G is equal to the trace of the orthogonal projection pi of the set support of G. So this means that basically to find the value of the character, we need to take the support of G and average over this support. So this simplifies a lot calculation of the character. Instead of group elements, we can consider a simpler object orthogonal projections. Next, we show that for any open sets, A and B inside of our space, we have that PA PB equal to PA union B. So let me point out that this is not some property which is true in general. So for instance, in the example which I explained before, if we have representation, the Koopman representation acting on L2 of xb with some invariant measure mu by shifts. So what orthogonal projection PA does, it takes a function on our space and averages over the set A. So it replaces the values on A by constant. If we apply then PB in case when B intersects A, so we take this segment, average it over it, and in general we obtain a different value in this segment. And so the function will not be constant on A union B. So we obtain a different result from the projection P A union B. So from averaging over the whole segment simultaneously. So this property is not true in general, but it's true for many cases for factor representations for each groups. And this basically means that we can deal with orthogonal projections similarly to Koopman sets. Now, one of important property of the trace on this orthogonal projection is continuity. So here are some technical details, but basically this proposition tells us that if we have Koopman sets A and B such that the ergodic measures, all ergodic measures are closed correspondingly, then the traces of this orthogonal projection PA and PB will be also closed. And the idea of the proof is that if this condition satisfied, we can find an element G of the group which will move G of B close to A, so with some small difference. So if we have some set A, some set B, close to this sense, then we have somehow move B like that, so that the difference, the symmetric difference will be small in the sense of measure, and this will allow us to prove this property. Next property is so also can be considered as continuity. So if we have a function f on the space of ergodic, almost ergodic measures, and if we have a sequence of functions MDN convergent to f, then the trace of this orthogonal projection will converge to some value dependent only on this function f. Using these properties, we can define a new function on the space of positive continuous functions with positive infimum and finite supremum as follows. So having a function f with values between 0 and 1 on the space of ergodic, almost ergodic measures, we can find a sequence of closed sets Bm as before, such that MBM converges to f. And then by previous proposition, we have that the value of the trace will converge to something dependent only on f, so we can define it as a function lower phi of f. And then if we have function capital F, which is now not necessarily with values between 0 and 1, it can have any positive values. We can write it as a ratio of two functions with values between 0 and 1, and define capital phi of f as a ratio of phi of f1 and phi of f2. The multiplicativity properties and other properties which we discussed before imply that these functions are well defined and coincide on the space of continuous functions with value between 0 and 1. Moreover, capital phi is continuous and multiplicative. So this follows from that property of multiplicativity of functions M A and of the trace. And having this, we need one more. So this is kind of a map which relates closed sets. So recall that closed set A define a function MA on ergodic measure, and from it we obtain a value related to the trace. So this way we relate closed sets to traces. Now we are ready to give a sketch of proof of the classification theorem. So recall that we want to describe all indecomposable characters on the commutator subgroup. Let capital phi be the corresponding function defined here. Using capital phi, we can define a new function by this formula, logarithm of phi of exponent of f. So this is just a transformation to make L to obtain a linear function. Now on this space of bounded continuous function. So from multiplicativity and other properties of phi, we deduce that L is a linear function. It's a continuous linear functional on a Banach space of bounded continuous functions on some compact. And so using Reed's Markov-Kakutani representation theorem, we obtain that there exists Ergodic measure nu defining this linear functional through integral, and coming back to the function capital phi, we obtain this formula that for any capital F, phi of capital F is exponent of integral of logarithm over this measure nu. So this is a bit messy object. We have space of ergodic measures, and on this space we are finding some measure to obtain this formula. Now, so what does this mean? For instance, what is interesting for us is when F equal to MA, so if F equal to MA, so this is a function of mu equal to the value mu of A, then this gives us, so f of mu will be just mu of A, so this is exponent integral logarithm of mu of A d nu. And on the right, what we have is just, so by definition, this is trace. So what you wanted to find, trace of the orthogonal projection averaging over the complement of the set A. So this way we find the relation between trace and ergodic invariant measures, which is already a step towards the proof of theorem 1, towards formula for the character. Next, so there is another technical step. To complete the proof, we show that this measure mu, in fact, is a very simple. It's a linear combination with integer indices of delta measures. But then, if you substitute the formula for mu here, so you obtain this integral will be just sum of logarithms of finite amount of measures of A with some multiplicator. So when you take exponent, you obtain exactly this formula. So we'll have what we wanted, phi of MA product of measures. Sorry for the technical difficulties. So the first part of theorem 1 was formula for the character of this form. So here next we just use what we so before that the value of chi of G is equal to the trace of E support of G, and we obtain the formula for the character for the composable character. So this is proves the first part of theorem 1. The second and third part are a bit also a bit technical. I will not show it here, but to give you an idea of the proof. So we show that in decomposable characters, satisfy some property of multiplicativity. So remember, if we have sequence of closed sets Bn, which in some sense converge to infinity, but such that ergodic measures converge uniformly to some value, that then we have that the measure of A intersecting with Bn converges to the product of measures, and moreover the traces converges to product of traces. So this is some multiplicative property, and it turns out if chi1 not equal to chi2 are multiplicative, then linear combination will not be multiplicative in this sense. By Cauchy-Schwarz inequality for some space, we can show that this is not possible. And so multiplicativity of a character automatically implies that it is it is indecomposable. Multiplicativity implies indecomposability. And finally, having so we showed that each indecomposable character have this particular form in terms of measures. To show the opposite side, that actually these characters exist, that for any integer numbers alpha 1 alpha k and any almost ergodic measures mu1 mu k, the formula from the theorem 1 gives the composable character, the character by the groupoid construction, which we saw at the beginning. So having a measure on some space. So this formula can be represented as some measure of fixed points. And we saw at the beginning that this function is a character because we can realize it using groupoid construction as a trace this formula pi of G psi for certain unit representation pi. This finishes the second part, and the third part, the description of characters on the group GB. So let me come back to the theorem. So we proved first part. I gave idea of the proof of the second, groupoid construction. And the third one is a standard consideration because the factor group is a simple object. It's an eliminable group. All its representations are just multiplicative homomorphisms to the unit circle. So all its representations are just one-dimensional representations. All irreducible representations, and from this we can derive this formula. Okay, and as I mentioned, an ongoing project is proving this result for the topological full groups. We have some sketch, but need to check the details. And that's all I wanted to tell today. Thank you.
Okay. Thank you for the nice talk. Are there any questions here or online?
Well, doesn't seem there are online questions.
So maybe then I have just one question. So this so how you can consider this Bernoulli diagram, then consider a group on it, a special group, and then you prove your theorem. This is about that your character is indecomposable. So is somehow, well, maybe I don't know, somehow are these Bernoulli diagrams, they appear naturally somehow in some dynamical systems as well, or so?
Yes, if you have a homomorphism of a Cantor space, you can so consider the topological full groups, and you can consider Kakutani-Rochlin towers, and they naturally lead to some Bernoulli diagram with this property that the approximately finite full group of this Bernoulli diagram will be a subgroup of the topological full group.
So then, what, in a sense, you're somehow considering like dynamical system, and then you using the properties of dynamical system, you can construct some nice group which has this nice property. And this is somehow possible maybe to go in the opposite direction, and if for some topological group if for some dynamical system you can construct some group in a similar way, and you know that this group has like this indecomposable character in some sense, then can you derive some properties, dynamical properties of this dynamical system? So something like go back is possible?
I think yes, basically. So we know that each ergodic measure, so for an action of group G with invariant ergodic measure, we obtain a character. We know complete description. So assume we know complete description of the characters. So it means that we know description of the values of this ergodic measure on, say, for instance, Klopen sets. So you obtain some information from knowing the character about the set of ergodic, or in general about the set of measures invariant on the action for group.
Okay, thank you. So are there no more questions? Let's thank the speaker again.
Okay, I'll finish. Oh.